Great, thanks Leon. It's good to be here across the street. So I want to start by explaining what I mean by this title, Making the Most of Seeing Nothing. And the situation we're looking at is quantum materials or condensed matter in general. One thing that I think makes it such an exciting field is that ultimately we're dealing with actual dirty pieces of dirt. But this dirt is interesting. So what it's made of is the basic constituents of a material. We have the periodic table, which gives us lots of combinations for materials we can make. We're mainly interested in what the electrons are going to do in these materials. And what makes the problem difficult is that these electrons are interacting with the Coulomb interactions and the laws of quantum mechanics. So in some sense, there's two types of materials we tend to play with. Some are just given to us, like a high-temperature superconductor forming a crystal. Or we can further engineer systems, for instance, in high-quality two-dimensional electron gases, or say at station Q, we're working on topological nanowires. So what we're interested in is how to relate, the details given to us into the UV, the particular materials, with all the sort of emergent phenomena which can occur when you look at low temperatures and long distances. So we know in the cuprates, for instance, we have superconductivity at high temperature. And these gallium arsenide devices, when you put it in strong magnetic fields, we get these beautiful fractional quantum Hall effects with emergent particles, which are neither electrons nor bosons. And other things can happen, like you can have emergent excitations, which are Dirac particles, which look like relativistic excitations. In condensed matter, we kind of want to be able to move both ways. Sometimes we're given the material in the UV, and we'd like to be able to predict, well, what's the emergent order that occurs? Or sometimes we have some idea for physics we'd like to see, and we'd like to be able to find a material which produces it. So this problem of sort of converting between the UV physics and IR physics is extremely difficult. So I think there's an interesting result from last year due to Perez, Garcia, Cubitt, and Wolf, where they can phrase it in a way which actually shows that to solve it in general is actually formally undecidable. So the way this is set up is they consider quite reasonable Hamiltonians, for instance, just spins interacting with nearest neighbors, and they ask, could there be a single algorithm which would solve this problem in general in order to predict a simple property like is it gapped or not? Are the particles massive? And they're actually able to show that this is formally undecidable in the same way that the halting problem is undecidable. So certainly doing this in complete generality is difficult, but we try and do it anyway. So it's very nice to have some general constraints on what phases could appear in these systems, what are possible phase transitions between them. So some of examples of constraints of this form, I have a couple famous ones here. So for instance, the C theorem, at least if we state it for quantum mechanics, says that if you look at the heat capacity of a one-dimensional quantum system, under RG flow it has to decrease. So if you take one critical point and perturb it, the heat capacity has to decrease. The generalization to higher dimensions is the F theorem. Another famous one is Luttinger's theorem, which says if you look at the volume of a Fermi surface, it's actually fixed by the microscopic number of electrons. Or the Merman-Wagner theorem, which says that if you have a continuous symmetry, it can't be spontaneously broken in one dimension. So the focus of this talk is going to be symmetry constraints. So it's another general constraint of this form. And the sort of question we're going to ask is, how do the symmetries of a system, for instance, the space group symmetries of the crystal the material is made of, what constraints they place on the nature of possible quantum ground states that can emerge? So it's interesting to contrast this with the classical context, where I don't think there's anything interesting you can say of this form. So let's consider, for instance, a classical system, which is an Ising magnet, where the states of the system are just specified by whether the spins are up and down. And the symmetry here is the Ising symmetry, which just flips an upspin to a downspin. So that's G. So if we ask the question at zero temperature, we're asking, what can we say about a symmetric classical state? Well, basically, there aren't any states which are symmetric classically, because if you apply the spin flip, it just changes the state. So we can only even try and answer the question at finite temperature, where instead of talking about states, we talk about probability distributions over states. Now, in this case, there's always a simple and obvious way to form a symmetric probability distribution, and that's just to make every single spin configuration equally likely. So this restores the symmetry, but there's nothing particularly interesting that the correlations have to do in this situation. But in quantum mechanics, it's quite different because we have a richer set of ways we can actually restore symmetries, and that's using quantum fluctuations. So suppose, again, we're at zero temperature, so we're talking about a single state. Quantum states, we can actually use superposition and entanglement. So for instance, suppose we want to make a quantum magnet which has Ising symmetry. So now each of the classical states becomes a state in the quantum Hilbert space, but because it's quantum, we can now superimpose using the superposition principle. So if we just superimpose all possible spin configurations, that's equivalent to a magnet which is actually polarized on the x direction. And this is now symmetric. So now even though there's no classical probability distribution, it's a single state, we can actually produce a state which is symmetric. And we'll call this a quantum pair magnet where we use quantum fluctuations to restore the symmetry. So as I impose more symmetries on the system, it's going to get harder to produce a state which is symmetric. So for instance, suppose rather than the Ising symmetry, I have a full SO3 symmetry, so the symmetries of a sphere. And now my spins, there's no real simple state you can make, because no matter how you point the spins, that spin state's going to break the SO3 symmetry. So the trick in this case is we need to use quantum entanglement. So what we can do is take two neighboring pairs of spins and enter them into a Bell pair. Now the Bell pair has the property that the two of them together are actually symmetric under spin rotations. So by entangling them this way, we restore the symmetry. So far it seems like we've used all the tools of quantum mechanics. We've used superposition and entanglement. But I want to argue that actually these two cases are not yet as interesting as they can be. And the distinction that has to be made is between entanglement, which is so-called short range, versus long range. So we see that this Ising pair magnet is a product state, just meaning that the full quantum state comes from taking a tensor product of the states individually. So there's no entanglement between distant spins. So this one has entanglement between nearest neighbors, but suppose we're willing to coarse grain and put on sort of blurry glasses, meaning let's just consider each two sites as being 1 degree of freedom. So once I do this blocking or coarse graining, again, the neighboring degrees of freedom don't talk, they're not entangled. So there's a sense in which these two are actually both product states. So the idea of a short-range entangled state is a state which is in the same universality class or is the same phase of a product state if you're willing to coarse grain. So that leads to one of the most basic distinctions between different quantum phases of matter. So if I consider all the possible quantum ground states, they come in two types. There's the types which are short-range entangled, which just means that they're in the same phase as a product state. And then there's everything else. And the interesting thing is that in quantum mechanics, there's many different distinct phases that can occur here. So the real question I want to ask in this talk is, when we demand a state is symmetric, could there be situations in which it actually forces the system to be long-range entangled rather than just short-range entangled? And why would having a constraint of this form be useful? So why do we even want to look for long-range entanglement? The reason is because you can think of it as an inherently quantum mechanical way to get universality. So as far as we know, there's basically two ways that a state can be forced to be long-range entangled. The first is if it's gapless, meaning that the excitations are massless. So in this case, it's somewhat similar to statistical mechanics, where we get universal power laws, and the universality lies in the exponents. In some ways, the more novel case is actually when the phase is gapped, and these are the so-called topological phases. So all the phases have finite energy. There's no power law interactions. But like in the case of the fractional quantum Hall effect, the emergent excitations are quite interesting. And that's because, say, in the case of 2 dimensions, there's so-called anyons. And what this means is that the emergent excitations have topological interactions. So for instance, in 2D, if you take one particle around another, there's a quantized Berry phase that's picked up. So now the universality is actually in these topological interactions, or universal braiding statistics. So this is the picture of what it looks like in 2 dimensions, and a big part of the field right now is figuring out what's the general form that these braiding and statistics can take in 3 and higher dimensions. Okay, so how might we try and force the system to be long-range entangled? So returning back to the spin system, so far by entangling nearest neighbors, I recovered SO3 symmetry, but I've clearly broken translation symmetry. So a natural question is to ask, well, what happens if I demand further that the system is translation invariant? So what we can do is try and play this trick again of using quantum superposition to restore the symmetry. So this is an idea due to Anderson, the so-called resonating valence bond states. So when I chose to put the system into these bell pairs, I had to choose which pairs to make. And there's obviously many different ways to do that. So what I can do is quantum mechanically superimpose over all the way to put the system into bell pairs. So when you do that, because the different copies can be related by translation, you restore the translation symmetry. So it's somewhat difficult to directly see from this picture why it's long-range entangled. But there's a somewhat nice picture for why the excitations are indeed these particles which aren't bosons or fermions. These are the so-called spin-on excitations. So what you could do is you could make a defect in the dimer covering where you leave one spin unentangled, but then put all the rest in bell pairs. And I'm drawing sort of one snapshot here, but really there's a superposition where this background of dimers is fluctuating. So this excitation is called a spin-on, and the beautiful property of it is if you take two of them and take one around the other, you find that it picks up a quantized Berry phase, which it doesn't actually have to be one. So the actual type of statistics that show up here, the phase, depends on, say, whether you use plus or minus signs here, or in general the sign structure. So there's actually many different types of quantum spin liquids which arise this way. So that restoring translation invariance forced the system to be long-range entangled is actually a famous result due first to Liebschultz-Mattis and then in 2 dimensions to Matt Hastings. So the statement, or at least how I'll state it here, is the following. If you have a spin system which is SO3 symmetric and translation symmetric, and if there's half-integer spin in each unit cell, then basically one of 3 things has to occur. One, it could be symmetry broken. There could just be spontaneous symmetry breaking. But otherwise, it either has to be gapless. So for instance, here, this is a spin chain compound where when you do neutron spectroscopy, and you look at the energy versus momentum relation for how the neutrons are absorbed, you find low energy excitations all the way down to 0 energy. So this is the gapless case. Or you might find that there's a spin gap, in which case what the theorem says that there actually has to be these anion excitations. So what's forbidden are these short-range entangled phases, which are morally like product states. So we know the answer to this first part is yes, there can be situations where restoring symmetry forces long-range entanglement. So why is this useful experimentally? Well, let's say we're given a material and we want to figure out roughly what type of phase it is. So I have the phases up here are the long-range entangled phases. They're either gapless or gap but long-range entangled. The other things it could be is, well, there could be symmetry breaking, or it could be one of these short-range entangled phases. So experimentally, what can we look at? Well, symmetry breaking is usually fairly straightforward to diagnose. Maybe not entirely straightforward, but there's things you can look for, like Bragg peaks, for instance, in scattering. Gapless has obvious thermodynamic signatures. You could look, for instance, at the heat capacity. But distinguish between these two is quite difficult. Both of them are gapped, so there's no signature in the heat capacity. Both of them are symmetric. The thing that distinguishes them is rather subtle. It's that the emergent excitations have these anionic statistics. So in principle, there's proposals for how you could directly measure these Berry phases. So for instance, in the quantum Hall effect, there's ideas for using these interferometry experiments. But these experiments are quite difficult. So in a sense, sort of the experimental situation is really pushing forward these direct studies here. But why are we trying to do this? Well, part of the reason is because we know from, for instance, this Hastings constraint that for some of these materials, these symmetry constraints actually tell us it couldn't be short-range entangled. So we know in these materials it should be long-range entangled, and that gives us the fortitude to keep trying these experiments. Okay, so what I want to do is, for the rest of the talk about 2 new types of symmetry constraints which go beyond the Liebschultz-Mattis and Hastings theorem I just discussed. So the first I'll call filling constraints, and the second are going to be point group constraints for quantum magnets. Okay, so the setup for the filling constraints is very general. We just have electrons. They're in a crystal. They're allowed to move around, so it's not just a magnetic model, but I'm going to assume the ionic potential is just fixed. Okay, so an elemental part of any condensed matter course is the band theory of metals, and that's one of the simplest examples of a filling constraint like this. So the filling is just defined to be the number of electrons in each unit cell of the crystal. So for instance, if I had this lattice here with one electron in each, I'll say nu equals 1. The symmetries in the problem are translation, which is defined by the unit cell, electron number conservation, and the spin of the electrons. So the criteria of band theory basically tells us that if the electron filling is even, we're going to be able to fill up each band completely with both an up and a down electron, and in this case it can be a band insulator. So a band insulator is an example of one of these gapped and short-range entangled phases. Whereas if you have odd filling, you can't completely fill a band, so you actually have to have a Fermi surface, and it's a metal. So because it's a metal, it's gapless and long-range entangled. Okay, but this picture, strictly speaking, only works if it's non-interacting, so what you'd like to do is generalize this kind of filling constraint when the interactions are arbitrarily strong. Okay, so what are the inputs for the constraint? Well, first I need to tell you what the symmetries are, and I want to use the most general symmetries of a crystal. So I'm going to have number conservation for the electrons, time reversal, and whatever the symmetries of the crystal are. So for instance, translation or reflection. Now you'll notice here that I'm not putting spin rotation symmetry, SO3. And the reason is generically spin isn't actually conserved in materials. There's spin-orbit coupling, where angular momentum is transferred between the orbital and the spin degree of freedom, so SO3 isn't preserved. But the reason we know that the fermions still had the spin attached to them is under time reversal, t squares to -1. So that's the Kramer's degeneracy. So this I will make use of. And then the other input I need from the material is just by looking at the chemical formula, you can count up the number of electrons in each unit cell nu. So the way I want to phrase it is, given the filling of the material, is it allowed to be symmetric and also short-range entangled? Or at that filling, does it have to be long-range entangled? So I want to say very briefly a little bit about crystal symmetries, because they're quite interesting. So addition into translation, if you're given a crystal, it could, of course, have other symmetries like inversion, symmetry, or reflection. It was actually an open problem for a while. If you try and classify all the different groups you can get from the symmetries of a crystal, how many are there in each dimension? Is it finite or infinite? So the question of whether it was finite was answered in 1911 by Bieberbach. He showed it's finite in any number of dimensions. The number of possible crystallographic symmetries that can arise grows very quickly. In 3D, there's 230. And I think it's kind of beautiful that nature actually decided to use all of them, so we have different materials in each of these 230 different space groups. So it's quite relevant to actually study what constraints could occur from all these different symmetry groups. Okay, so first I'm just going to state what the result of the filling constraint is, and it's going to be a big table, so you shouldn't try and memorize it. But the way I phrase it is the input is the crystal symmetry, either 1 through 230, and the filling of the material, and the output is whether it could be short-range entangled. So the result is as follows. The way you would use this table is you'd look at your material and say, okay, it's space group number 17. You'd count the number of electrons, and you'd see whether the number of electrons was a multiple of 4. So if the filling was a multiple of 4, then it could be short-range entangled. Otherwise, it has to actually be long-range entangled. So if you saw it was gapped and symmetric, it has to have these anion excitations. Now, the interesting thing here is whereas band theory would generally only tell us odd or even, a lot of the constraints here are actually, say, multiples of 4, 6, 8, and 12. So that tells us that we've got a more stringent criteria for something being short-range entangled than the band theory criteria. So, the materials which are most interesting are not the ones which are in this table, but the ones whose filling isn't allowed in this table, because those are the ones which have to be long-range entangled. Okay, so before discussing a rough proof of it, I'd like to give 2 applications of why a constraint like this is useful. The first are the iridate compounds. So these are 3-dimensional crystals. And what's known about them is If you look at the number of electrons in each unit cell, it's 12, so certainly a multiple of 2. So it's not an insulator, or it's not a Mott insulator in the usual band criteria case, because it has even filling. Experimentally, it's gapped and it's observed to be symmetric. There's no magnetic ordering down to very, very low temperatures. Maybe not absolute zero, but very, very low temperatures. And the other property in this material is it's very, very strongly spin-orbit coupled. So there's no spin rotational symmetry. So if you asked whether a phase like this had to be exotic, previously we wouldn't be able to say. So we can look back at this table. Well, the space group is 213. And for this space group, in order for it to be short-range entangled, the filling has to be a multiple of 8. Since the filling is a multiple of 12, we actually know if this doesn't order down to 0 temperature, it would have to be a spin-like group of the anyons. Okay, and another application I want to mention is how you could use a constraint like this to motivate materials discovery. So one thing people have been interested in very recently are these so-called topological semimetals. So the basic idea is many people are familiar with graphene, so a two-dimensional sheet. And if you look at the effective field theory for the graphene, it's basically the two-dimensional Dirac equation, the massless Dirac equation. So it's natural to ask whether you could generalize this to higher dimensions. Could we realize in some material the three-dimensional Dirac equation? So these are the so-called three-dimensional Dirac materials. One thing that's distinctive about them is if they're going to be governed by the Dirac equation, rather than being a Fermi surface, the Fermi surface has to be an actual single point. So in the last couple of years, a couple of materials like this have been found. For instance, this cadmium arsenide, where both numerical studies as well as ARPES show that indeed there's this dispersion relation here consistent with a three-dimensional Dirac equation. So what I'd like to ask is, can we use the filling constraints derived in that table to actually suggest many other materials which might be governed by this Dirac equation? So the idea is fairly simple. We need to look at materials which satisfy two things. So first, we want the filling of the material not to be allowed to be short-range entangled. All right, otherwise it could just be a band insulator. The other thing we do is we demand that the filling is actually even. The reason is if the filling was odd generically, there'd actually be a Fermi surface. But for these Dirac materials, we actually want a Fermi point. So if you can find materials which satisfy both of these, the band structure at least should be semi-metallic. So my collaborator, Adrian Poe, actually went ahead and tried to automate this procedure. So you can take a materials database and just all at once calculate for, say, space group 24 or 15, what are all the known materials which should be semi-metals according to this constraint. So you get some long list. You should do some basic chemistry checks, like if there's F electrons, it might be a Mott insulator rather than a metal. And then from that, you'd want to then do DFT on the material to see if the Dirac points are somewhere near the Fermi surface. So he's carried this out for 4 of the space groups. And I think it's kind of interesting to see how well this filling criteria works. So let's look, for instance, at space group 14. If you look in a database, there's 12,000 known materials with space group 14. And the filling criteria predicts that 500 of these could be these Dirac semimetals. So that was narrowing down by a factor of 20. The simple chemistry checks narrow it down by another factor of 10. And when they do DFT, 1/10 of those, like this material here, are actually new candidates to be Dirac semimetals. So the convenient thing here is they only had to do DFT on 50 materials rather than 12,000. So now I want to give a very rough, somewhat hand-waving argument for how these filling constraints were derived. So I'm going to do it in 2 steps. The first, I'm only going to use translation symmetry. And using translation symmetry, I'll recover the usual band criteria, which is that the filling has to be even. And then I want to use more general space group symmetries, so-called Nonce-morphic symmetries, to show that there can be tighter constraints. Okay, so here's how the argument works for translation. So I'm going to have to appeal to a certain principle that we think is true about short-range entangled phases. And that's if you take one of these short-range entangled phase and imagine defining the Hamiltonian on some system like a torus, which locally looks like the plane but is now compact, like the torus, it should still have a unique ground state. So short-range entangled phases should have unique ground states. Okay, so how can I use that to derive a constraint? So I'm going to argue by contradiction. So suppose you had a phase of these electrons which is actually at odd filling. Okay, so first I'm going to define the model on a torus. I can let the torus be arbitrarily large. So you can imagine Lx and Ly are much larger than any correlation length in the system. Now I'm going to choose the torus specifically to have odd by odd dimensions. The number of unit cells on this torus is odd. Okay, well, how many electrons are there going to be in the system? Well, the filling is odd and the dimensions are odd, so I know on this particular torus there's an odd number of electrons. But because electrons have this property that t squared equals -1, they carry Cramer's degeneracy. No matter what the interactions are, I know that the ground state on the torus has to at least be twofold degenerate. That's just Cramer's degeneracy. But this degeneracy contradicts this property of short-range entangled phases. If it was short-range entangled, it'd have to be a unique ground state. So degeneracy implies, in fact, it can't be short-range entangled. So we have a more rigorous way to prove this during entanglement using properties of the entanglement spectrum. But this one is quite easy to extend to nonce-morphic symmetries. So what is a nonce-morphic symmetry? So far I've only used translation symmetry. But there's a class of symmetries called nonce-morphic symmetries, such as screws and glides, which are defined as follows. So the glide symmetry, for instance, is a symmetry of someone walking down the beach. So the translational unit cell would take the right foot to the right foot, whereas the glide symmetry is you go by half a step and then apply a mirror reflecting left to right. So it's a combination of a half translation and then a reflection symmetry. So the space groups come in two types, the so-called symmorphic space groups. All the symmetries can be thought of as either as a product of a translation and then a point group symmetry. So a point group symmetry is a symmetry which leaves some point invariant, like a rotation. Whereas the non-symmorphic space groups, one of the generators has to be a screw or a glide. Non-symmorphic symmetries are quite general. Actually, most of the space groups are non-symmorphic. A common example, for instance, is the diamond lattice, which has a screw symmetry. So the fact that non-symmorphic symmetries can lead to tighter constraints was known in some simpler situations. So Zach actually studied this problem for free fermions when there's no spin-orbit coupling. And he found when you had these screws and glide symmetries and you look at the band structure, there tend to be high symmetry lines on which the bands stick together. And what that meant is that the fillings required to have a band insulator ended up being greater than multiples of 2. So for instance, if there's a band sticking, you'd actually have the filling be a multiple of 4. That's for free fermions. So I first learned about this problem from Sid Parameswaran, who's now at UC Irvine, and he wanted to generalize the study of Zach to the case where there are interactions but no spin-orbit coupling. And what he was able to show using a flux threading argument is that even in the presence of interactions for these non-symmorphic crystals, the filling had to be a multiple of 4 in order to be short-range entangled. Unfortunately, if we only have time reversal, there's no argument like flux threading that possibly works. So I want to instead use the trick I used for translation. Okay, so how do I make use of the non-symmorphic symmetry to get a more stringent constraint? Okay, so the idea is the following. I know somewhere I'm going to have to make use of the glide. Let's say I'm in 2 dimensions. So for instance, suppose I have this pattern of feet walking down the beach. One way to make use of the glide is to define the system not on a ring, but instead on a Mobius strip. So you can think of the Mobius strip as identifying the system modulo a glide, right? Because when you glue it back together here, the Mobius strip, you have to apply the reflection, which is defined in the glide. So the reason that's useful is if you look at the number of spins on the Mobius strip, even though each unit cell carries 2 spins, the Mobius strip will actually have an odd number of sites in it because you used the glide. So in 2 dimensions, the way I'll generalize this is to define the system on a Klein bottle. So I make it periodic in the y direction and then mod out by a glide in the x direction. And if you choose Lx to be odd and this to be odd over 2, we're guaranteed that the volume, the number of unit cells in this Klein bottle, is an odd number times an odd number divided by 2 because of this glide. So this allows us to actually get a contradiction with it being short-range entangled, even if the filling is a multiple of 2. So for instance, suppose the filling is twice an odd number. If I count the number of electrons on the Klein bottle, it's still going to be odd. That's because of this divided by 2 over here. So I'm still guaranteed that there's Cramer's degeneracy. Because there's Cramer's degeneracy, that principle tells me it can't be short-range entangled. So by using the glide, I've actually made the constraint twice as tight. So I'll just briefly say how this gets generalized to 3 dimensions. Well, so far I've used the torus and Klein bottle. How does this generalize to 3 dimensions? So the generalization of a torus and Klein bottle to 3 dimensions are going to be manifolds which are compact, so they have finite dimensions, but where everywhere it looks flat. And there's actually 10 manifolds like this in 3 dimensions. So one of them, for instance, is called the didicosm, as an interesting structure where, in the same way that you can think of a torus as identifying edges, in 3 dimensions you get the didicosm by identifying certain faces, but they're related together with twists, which give you a strange manifold. And what we're able to do is by choosing, by looking at the space group, you can try and choose the best Bieberbach manifold such that when you put the model on that, you get the tightest possible filling constraint. And we did this for each of the space groups, and that's how we arrive at all the constraints here. We think from doing this that this is actually the tightest possible filling constraint you could have for 220 of the 230 space groups. And there's 10 of them where we're not sure whether some other method could get a more stringent constraint. Okay, so far I've discussed system where the electrons are allowed to move around, and using only time reversal, we found were probably almost the most general constraints for ruling out short-range entanglement, and found that this can be useful for both guiding materials discovery as well as providing conditions in which, say, systems which are insulators would have to be long-range entangled spin liquids. So now I want to consider a slightly more restricted scenario, which is systems of quantum magnets. And now I want to focus on point group symmetries. So whereas in the last section I was allowing the electrons to move around, now I want to study so-called Mott insulators, where because of the strong interactions, the electrons actually get pinned to particular lattice sites. So their motion isn't so important, but the fact that electrons carry spin is, because now when they're localized in the site, they have a magnetic moment, and we have to decide how that magnetic moment, what sort of phase it's going to enter. So the effective models for these sorts of systems are quantum magnets. So I have lattices of spins interacting, for instance, with a Heisenberg interaction. So now I'm going to return to this situation of magnets and ask, well, what are the situations where I know there has to be long-range entanglement? Okay, so there's actually several results of this form. The first I told you about earlier was Hastings Theorem. And I can think of Hastings Theorem as sort of the first wave of a bunch of results. And what was particular about it is it only used translation symmetry, because all it counted was the spin per unit cell. To define a unit cell, you only use translation. So following up on that, there was the works of Sid, as well as a paper by myself and some collaborators. We generalized the Hastings constraint to the case of non-somorphic crystals. So these are ones with glides and screws. And you can think of that as just a special case of the result I just told you about. So, but none of these earlier results ever actually made use of a point group symmetry like a rotation or reflection. So for the remainder of the talk, I want to give what I think is the most general possible statement of this form using the full space group. Okay, so what's the input for this constraint? So again, I'm going to have a magnet, and the symmetry, at least for the purposes of this talk, I'll let it be SO3 and the space group. And I don't care too much about all the details of the material. The only thing I'm going to keep track of is the lattice of magnetic moments. And in particular, I don't even care whether the magnetic moment is spin 1/2 or, say, spin 3/2. So wherever there's a spin, an odd integer moment, I'll think of it as a black dot. whereas if it's an integer magnet at moment, I'll think of it as a white dot. So this is a kind of coarse graining of all the details into this simple lattice here. So now the question is, given your magnet defined on this lattice, you want to know whether it could be short-range entangled if it's symmetric. Okay, so here's a conjecture. The conjecture is that it's only possible to have a short-range entangled magnet if that lattice of spins is equivalent to a trivial lattice. Okay, so to make sense of this conjecture, I need to spend the next couple slides defining what do I mean by a trivial lattice and what do I mean by two lattices being equivalent. So here's the definition of a trivial lattice. A trivial lattice is a lattice of spins in which all of them are integers. So a simple case would be if you have a square lattice where each moment is spin 1. So what this conjecture is claiming is that if you define the spin 1 magnet, there needs to be some phase it could be in where it's actually short-range entangled. So that's actually rather surprising. As far as I know, all phases of a spin 1 magnet that have been discussed so far are actually either symmetry broken or are these long-range entangled spin liquids with anions. So first check we need to do on this conjecture is see, well, could there actually be a phase of matter of a spin 1 magnet which is just short-range entangled? So some of you might be familiar with the AKLT construction. So that's one particular way to get short-range entangled magnets. It actually doesn't apply here. So the AKLT only works if it had been spin 2 rather than a spin 1 magnet. And there's actually kind of theoretical reason why for a while I thought this wouldn't be possible. And it's related to Haldane's analysis of Berry phases, which is part of what he got the Nobel Prize for. So he was first studying spin 1 magnets, and he shows that there's a fundamental distinction between spin 1/2 and spin 1. So spin 1/2 had to be gapless, whereas spin 1 could be gapped. When he extended this analysis to 2 dimensions, he found the distinction was not between half integer and integer, but actually whether the spin was a multiple of 2. So in his analysis, to have a completely trivial magnet would actually have to be spin 2, which kind of agrees with this AKLT state here. So the usual interpretation of his analysis is that a spin 1 magnet would naturally actually have to break a symmetry, and in particular be a valence bond crystal. Okay, so this slide I want to tell you about a numerical check of this conjecture. And what we're able to do is numerically prove that there is actually, in principle, a phase of a spin 1 magnet which is just short-range entangled. So we can check the conjecture as long as we can provide like one state of a spin 1 magnet which is short-range entangled. We've checked the conjecture. So the way to do that is we need to write down some trial wave function for a spin 1 magnet. I won't get too much into the details, but there's been a nice development due to Frank Verstrata and Ignacio Sirac, which are the so-called tensor networks. And you can think of it as a sort of programming language for expressing any sort of many-body wave function or spin wave function. So what it does is it lets us, with a finite amount of information, propose a many-body wave function. The only caveat is that to check the properties of this wave function, you actually have to do somewhat complex numerics. So working with Chao Ming, we were able to propose what we thought was going to be a short-range entangled phase. And then by measuring the properties numerically, we're able to check 2 things. First, that indeed it's gapped, so all the spin correlations are exponentially decaying. The symmetries are preserved, so we can see that by looking, for instance, at spin-spin correlation functions. And second, we need to check that it's really short-range entangled. So there's a nice result from Kataev, Preskel, and Levin and Wen, which actually gives you a numerical criteria to prove that a magnet is short-range entangled. It's the so-called topological entanglement entropy. And we do numerics on various size systems, and we're able to show, indeed, that it's short-range entangled. So this is just a numerical check that the conjecture could be true. Okay, so far I've defined what a trivial lattice is. The other part of the conjecture, I need to define what do I mean for 2 lattices or 2 magnets to be equivalent. Okay, so let me define an equivalence relation between 2 lattices.
Sorry, so
yeah.
Is it possible that a spin sector is gapped at the spin sector because gapping?
Yeah, so I phrase it as if I only looked at spin-spin. We're actually able to bound all possible correlation lengths and shows that it's finite. So there's no dimer-dimer correlations or anything like that either. So that's another thing that tensor networks let you do. You can sort of in one shot bound all possible correlations. Okay, so here's the rules of the equivalence relation. So the first is that if you have two lattices that you can relate to each other by just smoothly moving the spins around, such that throughout that process you preserve all the spatial symmetries. So in this case here, I have a C3 symmetry and a mirror about this line. Then I'll say that the two lattices are equivalent. So here, for instance, if I had two spins, whenever I move this one, its mirror image has to move in a corresponding way. Now, as you're moving them around, it's very natural for two spins to come and collide with each other. And the rule I'll use is that when they collide together, it's just Z2 fusion. So that just means that if two half-integer spins come together, it gives me an integer. So two blacks turn to a white, likely two whites turn to a white. Whereas if an integer and half-integer come together, it leaves behind a half-integer. So as you're doing this process, it's very natural on high symmetry points for some number of spins to come together and annihilate in that way. So if two lattices are related by these two rules, I say they're basically the same lattice for the purpose of this classification. So let me carry this out, for instance, for the spin 1/2 honeycomb lattice. So imagine to start, I had a magnet which was a bunch of spin 1/2s on the honeycomb. So I can use the first move, or the second move, and split this site into 3 sites, because I only need to conserve the parity. And then I move along the bonds of the honeycomb, and then they annihilate on what's actually a Kagome lattice. And when they annihilate, it's 2 going into 0. So what this shows you is that the spin 1/2 honeycomb is equivalent to an integer spin Kagome. So according to my definition, then, I'll say that the spin 1/2 honeycomb lattice is actually equivalent to the trivial lattice, which means that I'd be conjecturing that if you have a magnet which is spin 1/2 honeycomb, in principle, there's some phase where it's short-range entangled. So like the spin 1 case, no one had written down an example of a spin 1/2 magnet which was short-range entangled on the honeycomb. But working with Ying Rang's group, we did a similar tensor network calculation. We're actually able to show that there are trivial magnetic phases on the honeycomb. One of the consequences of this is actually for graphene. So normally when we think about graphene at empty filling, people talk about it either being gapless or possibly having some sort of symmetry breaking. But this tells you that with strong interactions, in principle, graphene could actually just be an interacting insulator, which is completely symmetric and short-range entangled. Okay, so to restate the lattice classification, basically say that given a group, we have an equivalence relation on lattices, and that means I can talk about equivalence classes of quantum magnets. Formally, it's a kind of interesting mathematical structure. So these equivalence classes actually form an abelian group where the operation is stacking 2 lattices on top of each other, where the identity element is just the completely empty lattice. So in this form, the conjecture is that a magnet can be short-range entangled only if it's in the trivial equivalence class. Any other magnet has to be a long-range entangled spin liquid. Let me give one example of a lattice where this constraint applies, where we didn't have a constraint before, and that's the lattice relevant to spin ice compounds. So these spin ice compounds, you have a set of moments on the so-called pyrochlore lattice. They have this constraint, which you've probably heard about from Leon, which is this 2 in, 2 out. And at least at finite temperature, it's known that the thermal fluctuations actually cause it to enter this liquid phase, which is effectively like quantum electrodynamics. So there's these monopole excitations which interact with long-range interactions. So, it's interesting to ask, well, if we take the system down to 0 temperature, what constraints could there be if symmetry is conserved? So the first thing we can do is count the number of moments in the unit cell and ask, let's look at all the earlier constraints from Liebschultz-Mattis or Hastings or the one I talked about earlier. Does the system even have to be long-range entangled? And if you look at the space group of pyrochlore, it's 227, you'd find that it can be short-range entangled if there's any multiple of 4 moments in the unit cell. And actually for the pyrochlore lattice, it is a multiple of 4. I think it's 8 or 16. So with all the existing results, there's not actually a constraint on this material. It could be short-range entangled at 0 temperature. So we can calculate this equivalence relation for 227, and we find that there's actually 16 distinct types of lattices that occur for this space group. So our constraint says that 15 of these lattices can't be short-range entangled. And if you look at the pyrochlore lattice, the one that's defined for spin ice, you actually find that it's a non-trivial entry here. So while according to the previous constraint, it could be trivial, using these point group constraints, it actually has to be long-range entangled. So you then know that as you cool this spin ice towards low temperature, it either has to be a long-range entangled phase, in which case we'd call it the quantum spin ice, or it has to order in some fashion. So there's certain subtleties here about whether the proof works with spin-orbit coupling. It does, yeah. I mean, our proof does actually apply for the simplest spin ice Hamiltonians. So hopefully we can generalize it to all the details. So I'm not actually going to prove the conjecture here. I've called it a conjecture because we have a way to prove it for all the space groups in 1 and 2 dimension. So it's a sort of generalization of flux threading arguments. But for 3 dimensions, we have 230 cases to deal with, and we've proved it for 80% of them, roughly, and there's 20 of them which we don't, or 20% which we don't yet have a technique for proving this conjecture. So I think it's probably going to be true in general, and we're looking for some new techniques now to prove it in generality. Okay, so that concludes the part on point group constraints. So the nice thing about this is it vastly increases the number of quantum magnets that we know have to be long-range entangled. And I think that this sort of statement in terms of this equivalence relation is probably the most general form that all these symmetry constraints should take once they're phrased properly. Okay, so with that, all the 2 works here with my collaborators, Adrian and Poe did a lot of the work, as well as Haruki and Ashvin while I was at Berkeley, and Chao Ming, who's here at KITP. And there's a number of related works which also talk about constraining the type of spin liquids that can emerge in these systems, and that's with my collaborators at Station Q. So thanks.
Thanks for a beautiful talk. Time for questions? Gary?
Yeah, when you were giving us an idea of how you prove this sort of second thing about the filling,
Yeah.
You referred to a principle about uniqueness.
Yeah.
Is that something you actually prove in your proof?
So you can prove it, yeah. So if you make a somewhat simpler definition of short-range entangled phase, which is one more restricted way to define short-range entangled is that you can build a short-range entangled ground state by acting with a finite depth quantum circuit, so like some number of nearest neighbor unitaries. That's maybe a more restrictive definition than necessary of short-range entangled, but if you take that more restrictive form, you can prove an assumption like that. More generically, we think that rather than using strictly like local unitaries, they should be allowed to have exponential tails and so on. And in that case, I don't know how to prove it rigorously. But it's generally, I mean, some people would define short-range entangled to be unique ground state on any manifold. So it's a little bit about what your starting point is for defining short-range entangled and showing that those are equivalent. Yeah. Yeah. There's probably two. Well, okay. There's two cases. One case which I think is interesting is, let me go to the very dilute limit. Suppose I had some lattice like this, and imagine the dilution is very dilute compared to the correlation length. You can then ask, suppose there's a disorder which is, say, like a substitution, so replace a spin 1/2 by a spin 1. I haven't talked about it here, but this constraint actually will tell you something interesting, or a version of it, that there has to be degeneracies that get bound to those dilutions. I mean, of course, if what happens is the dilutions are very small compared to any correlation length, and you just don't have a symmetry to talk about, in which case nothing really prevents it from just forming kind of some random valence bond solid. I think an interesting case is if you said, suppose the disorder is like statistically on average translation invariant. I think it could be that a conjecture like this still holds, but I don't know how to prove it then.
I have a question, comment related to the first question about the uniqueness of the short range.
Yeah.
There is this, like Kugel-Homsky type spin orbital models, and for spin 1/2 degrees of freedom, and you can define them on a bunch of lattices in 2D and 3D, and you can construct the exact ground state, which will be a product state of timers, and have this ground state will have a massive degeneracy with respect to the dimer covering, hardcore dimer covering of those.
So is it completely generic as you add perturbations, it doesn't lift the degeneracy?
Well, if you add the perturbation, it will.
Yeah.
It will no longer be the exact ground state.
Yeah.
But, I mean, you can define the model which has exact ground state, which has massive degeneracy. Quantum problem.
Right. Yeah, so I think when I say, so if I say short range entangled phase has unique ground state, we'll have to define some notion of stability that, if you, like in that case you were saying, if you add some small generic perturbation, it actually lifts the degeneracy you were talking about. So you want to talk about generic degeneracies which couldn't be lifted by any perturbation.
Yeah, so can you go back to the slide about particle lattice again?
Yeah.
Yeah, so here we have two results, right? So the first result is for electron system, second is for spin system, right?
Yeah.
So you're saying, and the first result cannot be applied to interacting electron system?
This can be applied even if it's interacting. Yeah.
The second one should also be viewed as interacting electron system.
Yeah. Here, yeah. So maybe your question is really, did I really have to assume in this case that it was a magnet, like the degrees of freedom were spins? So you could ask, suppose in this magnet you actually think of it as electrons and allow them to hop.
Yeah.
At the moment, I think the constraint is you lose this constraint. So it's actually important that you can think of it as local moments rather than as electrons with, at least as I've proved it. I mean, there should be some way, because I mean, ultimately a magnet comes from spinful fermions to release that, to allow them to hop, but I don't know how.
So somehow there's some incompleteness about the first table?
Yeah, so basically this table, the only input was the symmetry group and the filling. It says nothing about where the lattice points are. Whereas this one is all precisely about not just the symmetry group, but where are the actual spins. That's what this equivalence relation is dealing with. So there's more information here that you know where the moments are, and that's why you can get a more stringent constraint. So I think it's an interesting question. Is there a way, if you take into account that in these systems the electrons are actually, virtually fluctuating, is there still a precise way to say where the moments are in space, even though there's some charge fluctuations? I would guess that as long as you have a charge gap, there's still a precise way to say these are where the moments are.
So in your the spin 1 square lattice, we had this wave function with the tensor product states. Is there something you can say about the sign structure of that wave function? That's one question. And the other is, you have guesses for Hamiltonians that might have ground states that are short-range entangled.
Yeah, so I can... Actually, yeah, the picture for what the state is, I can say it in words, actually. So, normally the way you do an AKLT type construction is you first imagine that your site, rather than being spin 1 or spin 2, is actually 4 spin 1/2s. Let me go back to this AKLT picture. Yeah, so for the usual AKLT, you assume each spite actually has 4 spin 1/2s. The neighboring spin 1/2s you just project into a bell pair. And then you notice that, well, if I have 4 spin 1/2s, if I fuse them together, sitting in there somewhere is a spin 2. So this state we were talking about, in the fusion of 4 spin 1/2s, there's also 2 spin 1s in there. One of them breaks the symmetry, but there's a way to embed spin 1 which preserves all the lattice symmetries. So the state itself isn't actually that complicated. Normally with these oftentimes with tensor networks, you can derive a so-called parent Hamiltonian. So it's like a model wave function where it's the unique ground state. That requires some technical assumption that the tensor network's injective, something like that. And this one isn't. So we can't actually prove it's the unique ground state of some particular Hamiltonian. But in principle, you can imagine, since you know exactly what the spin correlations are, to try and just engineer, some Heisenberg Hamiltonian which would have the best energy for that sort of spin-spin correlations. So probably there's some J1, J2, J3 where you can stabilize this, but I haven't.
Some idea how one might get into that phase from some ordered state, or?
It's not. Oh, you mean in a field theory, like it's some field theory? I don't actually. I guess what we know from Haldane's analysis is there's probably no easy way to access it from the nonlinear sigma model, probably, at least as far as I know. Yeah, so I don't actually have a field theory for this phase yet.
Again, in the spin 1 case, is it true that the wave function still can't be adiabatically connected to a product state while preserving the symmetries? Can we use it as symmetry protected?
Yeah, for this particular wave function we wrote down, if you now ask about, okay, we talked about classification and presence of symmetries, is it a symmetry protected topological phase? Then it would be yes, it would be non-trivial. I think you can actually write down an even more general thing, which is just completely trivial. Isn't even an SPT.
So going back to the first part of your talk, I have a very simple-minded question. You sort of said it was kind of trivial to count the number of electrons. Is it always trivial? Or are there cases where you have configuration interactions where the valence is not well defined?
Well, I'm not sure if the valence you're thinking of is really being, it's just a transfer. But if you're just trying to count the number of electrons in the unit cell,
count the number of electrons,
yeah.
But you're only counting those you're not counting all of them.
No, you actually just count all of them. So even if they're like deep in the core, you just count them. So it really would just be, you look at the chemical formula unit, add up the atomic numbers, and so that's the filling. So it doesn't really matter valence versus conduction.
So it doesn't matter.
Yeah, you just add them all up.